type a message, you hit send, and for a fraction of a second, that tiny bubble launches forward, and then reality stops. That text hasn't reached the internet yet. It hasn't even left your phone. Right now, it's sitting inside a microscopic processing facility deep within your device. To get from your screen to a friend's pocket, this data must pass through a strict 7-member delivery team. Nobody on this team handles the whole journey. Each specialist executes one exact job, then hands the package down to the next station. This compartmentalized assembly line is known as the OSI model. Tracking a single message through these 7 stages reveals the structural logic required for the modern internet to function. The journey starts at layer 7, the application layer. This is the only station that actually understands human intention. It recognizes the specific app you're using and the communication protocols that app requires. It strips away the visual interface, the colors, the chat bubbles, the fonts, and translates your raw text into a structured data object, attaching metadata to identify exactly where this information originated. That object slides down to layer 6, the presentation layer. Think of this as the network's shipping department. It standardizes the file format so any computer can read it, and compresses the data to shrink its physical footprint. Then it encrypts the information. It scrambles the text and locks the entire package inside a secure mathematical shell, rendering the contents unreadable to anyone trying to intercept it in transit. Before a single piece of hardware is engaged, these first 2 layers have successfully translated a human thought into a secure, universally readable digital container. Before sending that container into the void, the sender and receiver need to agree to talk. Layer 5, the session layer, reaches across the network to open a dedicated communication tunnel. While the data is ink-repaired, this layer maintains a continuous digital heartbeat. It pulses a persistent signal back and forth to ensure the connection stays open and ready. Now the data reaches layer 4, the transport layer. And here, the system does something highly counterintuitive. The system slices the message into smaller, identical fragments called packets. Moving thousands of tiny, numbered pieces is more reliable than moving a single large file. Because the transport layer stamps each packet with a sequence number, they don't even have to take the same path. They can travel completely independently through the network. If a piece of infrastructure fails and a packet gets lost, the receiver simply checks the sequence numbers and asks for that specific missing piece to be sent again. To find their way, these packets drop down to layer 3, a network layer. This acts as a global navigation system, permanently stamping the final destination's IP address onto every single piece of data. As the packets hit routers, the massive intersections of the internet, each router reads that IP address, evaluates the traffic ahead, and dynamically alters the path to bypass congestion. But a router only knows the general direction. It passes the packet to layer 2, the data link layer. This layer ignores the global map entirely, focusing strictly on the physical jump to the very next piece of hardware. For every individual jump from a phone to a modem or a modem to a server, this layer applies a temporary, hardware-specific MAC address. The moment the packet completes that single hop, the tag is replaced for the next jump. During each transfer, layer 2 quietly scans the packet for localized corruption. If the data was damaged between devices, it requests a replacement before the packet moves forward. This separation of labor is why the network can handle global traffic volumes. The network layer manages the thousands of miles across a continent, while the data link layer manages the precise handoff across the final 10 feet. At the bottom sits layer 1, the physical layer. Down here, the packets, the software labels, and the encryption keys cease to exist as digital objects. The device's transmitter converts those digital ones and zeros into raw physical energy. It blasts electromagnetic radio waves through the air, or fires rapid pulses of light down glass fiber optic cables. Despite the complex software logic working above it, the global internet is ultimately constrained by the physical properties of light and energy moving through reality. When that energy reaches the destination, the entire process runs in reverse. The receiving antenna catches the raw signal at the physical layer and translates it back into digital bits. The data link layer strips the final MAC address.
The network layer confirms the IP destination. The transport layer catches the incoming packets, lines up their sequence numbers, and stitches them back into a single block, while the session layer validates the active connection. The presentation layer dissolves the protective encryption shell and unpacks the compressed data, sliding the raw text up into the application layer to be formatted for the screen. And in that exact fraction of a second, reality snaps back to normal speed. The OSI model dictates this exact sequence for every single interaction on the web. It is the invisible, choreographed assembly line that translates a human thought into raw energy, sends it across the globe, and turns it back into a thought on the other side.